Our universe is a puzzle with countless missing pieces. For centuries, scientists have worked to fill in the gaps, but the picture remains incomplete. We've mapped galaxies, detected gravitational waves, and photographed black holes. Yet these discoveries have only led to more questions. Join us today as we delve into everything we don't know about the universe. Music, the concept of what came before the Big Bang, intrigues many, yet it also presents a significant challenge to our understanding of time and space. The Big Bang, occurring approximately 13.8 billion years ago, marks the inception of our universe as we know it, leading to the expansion of space-time and matter. However, the nature of reality prior to this event is shrouded in mystery, as standard models of physics struggle to describe a time when the universe did not exist. Some theories suggest that before the Big Bang, the universe could have been in a singular state, an infinitely dense point where conventional physics breaks down. Others propose that our universe emerged from a previous cosmic event, or it could be the latest iteration in an infinite cycle of expansions and contractions. In this cyclic model, the universe undergoes a series of big bangs and big crunches, where after each contraction, it experiences another expansion. Another fascinating idea is the multiverse theory, proposing the existence of multiple, perhaps infinite, universes, each with its own unique laws of physics. Under this perspective, our Big Bang could simply be one event among countless others occurring simultaneously in a vast and varied cosmos. Each universe within this multiverse might have a different origin, leading to entirely different configurations of matter and energy. These theories highlight the limits of our current understanding and the complexity of the cosmos. While we may not possess definitive answers to what preceded the Big Bang, the exploration of these ideas fuels the journey of scientific inquiry, urging us to look beyond the boundaries of our universe and question the very fabric of existence. The question of why the Big Bang occurred continues to puzzle scientists and cosmologists as it delves into the deepest mysteries surrounding the origins of our universe. The Big Bang theory is widely accepted as the best explanation for the initial expansion of the universe, but it does not provide a definitive answer about the underlying cause of this monumental event. The circumstances that led to the Big Bang remain largely speculative and are the subject of ongoing research. One popular idea within cosmology is that quantum fluctuations in a vacuum could have given rise to the Big Bang. In the realm of quantum physics, fluctuations can occur even in empty space, where particles and antiparticles may appear and then annihilate each other in a fleeting moment. Theories in this domain suggest that a significant fluctuation might have triggered a rapid expansion, leading to the formation of our universe. This process could provide insight into how the fabric of space-time itself may have evolved. Another perspective focuses on concepts such as cosmic inflation. This theory posits that a brief exponential expansion followed the initial singularity, smoothing out irregularities and setting the stage for the universe we observe today. While inflation explains how the universe expanded rapidly just after the Big Bang, it does not address the fundamental question of why the Big Bang happened in the first place. Many cosmologists also consider the possibility of a pre-existing state or alternate framework in which our universe exists. This approach may suggest that our universe is just one of many that emerge from an intricate interplay of physical laws beyond our current understanding. While much research remains to be done, exploring these questions is crucial for grasping the origins of everything we know and the overarching structure of reality itself. The emergence of the laws of physics from the Big Bang is a profound aspect of our understanding of the universe. At the moment of the Big Bang, approximately 13.8 billion years ago, the universe was in an extremely hot and dense state. It was during this early period, known as the Planck era, that the fundamental forces of nature began to take shape. These forces include gravity, electromagnetism, and the strong and weak nuclear forces, which are the cornerstones of modern physics. As the universe expanded and cooled, the fundamental particles that constitute matter began to form. Initially, the universe was a chaotic soup of quarks and gluons. However, as temperatures dropped, quarks combined to form protons and neutrons, signaling the onset of what we might consider the building blocks of matter. This phase transitions into the formation of atomic nuclei during nuclear synthesis, which occurred a few minutes after the Big Bang. The subsequent cooling allowed electrons to join with protons, forming neutral hydrogen atoms, leading to the creation of the first atoms, which would later combine to form stars and galaxies. The laws of physics, as we perceive them, stem from symmetries and conservation principles that govern these fundamental forces and particles. For example, the theory of quantum mechanics and the theory of relativity play pivotal roles in determining how particles interact and how gravity operates on a cosmic scale. The unification of these forces into coherent laws is a field of ongoing research, particularly in the quest to formulate a grand unified theory that can describe all forces under a single framework. While we have made substantial advancements in understanding how the laws of physics emerge and operate, many questions remain. The early universe's conditions were so extreme that they defy our current physical theories. Events such as the unification of forces and the behavior of matter and energy at such high energies necessitate new theories. Grasping these complexities not only deepens our comprehension of the cosmos, but also invites us to explore the very foundation upon which reality is constructed. The initial imbalance between matter and antimatter is one of the most intriguing puzzles in modern cosmology and particle physics. According to the laws of physics, for every particle of matter, there should exist a corresponding particle of antimatter, which is identical in mass but opposite in charge. In the moments following the Big Bang, it is believed that equal quantities of both matter and antimatter were created. Nevertheless, our universe is dominated by matter, with only trace amounts of antimatter detectable today. One possible explanation for this imbalance lies in a phenomenon known as baryogenesis. This concept refers to the processes that may have led to an excess of baryons, the family of particles that includes protons and neutrons, over antibaryons. Various theories suggest conditions in the early universe that could have favored the production of matter over antimatter. For instance, certain interactions and decay processes might allow for the violation of symmetries, specifically a property called charge parity violation. This indicates that the laws of physics could behave differently for matter and antimatter under specific conditions. Experiments, particularly those involving particle accelerators, have been vital in identifying CP violation. Observations of certain decays involving particles called kaons and B mesons demonstrate that these violations exist, suggesting that they could contribute to the slight excess of matter. However, these observed effects alone cannot account for the vast disparity required to explain why our universe is largely composed of matter. Another avenue of research explores the role of inflationary theory, which proposes a rapid expansion of the universe shortly after the Big Bang. During this phase, any remaining antimatter could have been diluted or driven apart from matter due to inhomogeneities in the distribution of energy and matter, leading to regions dominated by matter. As we delve deeper into these concepts, we edge closer to unraveling the mystery of the asymmetry that shapes the cosmos and ultimately defines the very nature of our existence. The formation of the first atoms in the early universe is a fascinating process that unfolded during a period known as recombination. This event occurred roughly 380,000 years after the Big Bang, when the universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms. Prior to this era, the universe was an incredibly hot and dense plasma composed primarily of quarks, gluons, protons, neutrons, and electrons, making it opaque to radiation due to frequent interactions among particles. As the universe expanded, it gradually cooled. When the temperature dropped to about 3,000 Kelvin, electrons were able to combine with protons without being immediately ripped apart by high-energy photons. This process of recombination allowed for the formation of the first stable hydrogen atoms. Once these atoms were formed, the universe became transparent to radiation, leading to the release of the cosmic microwave background radiation, which we now detect as an echo of this primordial event. In addition to hydrogen, a small fraction of helium was formed during nucleosynthesis, which took place within the first few minutes of the universe's existence. In this process, protons fuse to create helium nuclei alongside trace amounts of lithium and beryllium. Most of the universe's helium was created during this nucleosynthesis phase rather than through subsequent stellar processes. The emergence of these first atoms marked a critical point in cosmic history. Not only did this transition lead to the universe becoming transparent and enabling the formation of light, but it set the stage for the subsequent development of stars, galaxies, and the intricate structures we observe today. As stars formed, they fused hydrogen into heavier elements, enriching the universe with a variety of elements that are essential for life as we understand it. This process highlights the remarkable journey from the simplicity of a hot plasma to the complex, structured universe we inhabit many billion years later. Music. The nature of dark matter remains one of the most perplexing questions in contemporary astrophysics. Dark matter is an invisible substance that does not emit or absorb light, making it impossible to detect directly through conventional means. Its existence is inferred from its gravitational effects on visible matter, radiation, and the large-scale structure of the universe. Approximately 27% of the total energy density of the universe is attributed to dark matter, yet its composition continues to elude scientists. One of the leading candidates for dark matter is a category of hypothetical particles called weakly interacting massive particles, WIMPs. These particles are predicted to have mass, but interact only through the weak nuclear force and gravity, making them extremely difficult to detect. Various experiments are ongoing to find evidence of WIMPs using underground detectors, particle accelerators, and other advanced technologies. If discovered, WIMPs could provide crucial insights into the true nature of dark matter. Another potential candidate is axion, extremely lightweight particles that might also account for dark matter. Axions are predicted by certain theories of particle physics and could generate weak signals detectable by specialized experiments, like WIMPs. Axions would have only minimal interactions with ordinary matter, making them hard to identify. The search for axions involves innovative techniques, including the use of strong magnetic fields to convert their hypothetical presence into detectable photons. Current research also considers alternatives to particle candidates. Some theories propose that dark matter might be related to modifications in gravitational theory itself, such as modifications to Einstein's general relativity. These alternative explanations challenge the traditional view of dark matter and open the door to new physics. The quest to uncover the true nature of dark matter not only promises to deepen our understanding of the cosmos, but may also redefine our grasp of fundamental physics. As experiments continue, the answers could revolutionize our comprehension of the universe and the mysterious forces that govern it. The inability to directly observe dark matter is rooted in its unique properties that differentiate it from ordinary matter. Dark matter does not emit, absorb, or reflect light or any other form of electromagnetic radiation, which makes it invisible to the conventional means of observation that astronomers typically employ. Our telescopes and instruments, which are adept at detecting various forms of light, simply cannot perceive anything that does not interact with electromagnetic forces. The nature of dark matter suggests that it primarily interacts through gravity. While ordinary matter clumps together and forms stars, planets, and galaxies, dark matter forms a framework around which visible matter organizes. This gravitational influence can be observed through phenomena such as the rotation curves of galaxies, where stars on the outskirts move faster than expected based on the visible mass alone. Additionally, dark matter's presence can be inferred from the gravitational lensing of light from distant objects, which reveals the curvature of space caused by its mass. These observations allow scientists to map the distribution of dark matter without actually seeing it. Furthermore, current theoretical models propose that dark matter might consist of particles that interact very weakly with regular matter. This weak interaction makes it challenging for experimental setups designed to detect these particles to succeed. Various experiments are attempting to identify potential dark matter candidates, such as weakly interacting massive particles and axions, but they require precise conditions and sophisticated technology to create or detect the elusive signals these particles might produce. The quest for understanding dark matter emphasizes the limitations of our observational tools and the necessity for innovative approaches to physics as we continue exploring the universe and refining our technology. The hope remains that we will one day pierce the veil of darkness that surrounds this enigmatic substance and reveal its profound implications for the cosmos. Dark matter interacts with regular matter primarily through gravity, which is fundamentally different from how ordinary matter interacts with itself. While regular matter exerts electromagnetic forces, allowing atoms to bind together and form complex structures, dark matter's interactions are solely gravitational. This means that although dark matter may not be directly visible or detectable through light, its gravitational influence is significant and can be observed in various cosmic phenomena. The effects of dark matter on regular matter can be seen in the behavior of galaxies. When astronomers measure the rotation speeds of stars and galaxies, they observe that stars on the edges rotate much faster than what would be expected based on the visible mass. This discrepancy indicates that there is likely a significant amount of unseen mass attributed to dark matter, exerting gravitational pull on the stars. This phenomenon led to the realization that dark matter constitutes a considerable portion of the overall mass within galaxies, helping to hold them together. Moreover, dark matter also plays a crucial role in the large-scale structure of the universe. It forms a scaffolding of gravitational wells that facilitates the formation of galaxies and galaxy clusters. As matter clumps under the influence of gravity, dark matter provides the necessary gravitational pull to aid in the collapse of gas and dust into stars and galaxies. This interplay between dark matter and regular matter shapes the cosmic web, influencing the distribution of galaxies across vast distances. Current research also explores the possibility of other forms of interaction between dark matter and regular matter. Some theories suggest that there might be additional, albeit extremely weak, interactions through forces beyond gravity. Although these have not yet been confirmed, investigating these potential interactions could redefine our understanding of both dark matter and the fundamental forces of nature. The ongoing pursuit of this knowledge sheds light on the complex relationship between dark matter and the visible universe, revealing the intricate mechanisms fueling cosmic evolution. The accelerating expansion of the universe, initially surprising to scientists, is primarily attributed to a mysterious phenomenon known as dark energy. Discovered through observations of distant supernovae in the late 1990s, this acceleration suggests that the rate at which the universe is expanding is not just increasing, but doing so at an ever-accelerating pace. Dark energy is believed to constitute about 73% of the total energy density of the universe, yet its exact nature remains elusive. One of the leading theories regarding dark energy posits that it is a constant energy density inherent to the fabric of space itself, often referred to as the cosmological constant. This idea originates from Einstein's equations of general relativity, which originally included a term to account for a static universe. When it was found that the universe was expanding, this term was discarded. However, the discovery of the universe's acceleration revived interest in this concept, suggesting that as space expands, more dark energy is created, perpetuating the acceleration. Another possibility is that dark energy could represent a dynamic field that changes over time, rather than being a constant value. This leads to alternative theories, such as quintessence, which suggests that dark energy may have varying energy density at different epochs of cosmic history. Such models offer a broader perspective on how the universe evolves and how dark energy might influence its ultimate fate. The implications of the accelerating expansion are profound and raise fundamental questions about the future of the universe. If dark energy continues driving the acceleration, it may lead to scenarios like the Big Freeze, where galaxies drift ever farther apart, ultimately leaving a cold, empty cosmos. The search for understanding dark energy remains one of the biggest challenges in modern cosmology. As research continues, Unlocking the secrets of dark energy could reshape our comprehension of the universe and the underlying physics that governs its evolution. The nature of dark energy, whether it is constant or changes over time, remains a significant question in cosmology. The simplest model of dark energy is known as the cosmological constant, which posits that dark energy has a uniform energy density throughout space and time. This concept was initially introduced by Albert Einstein in 1916 as part of his theory of general relativity. When it was later determined that the universe was expanding, the cosmological constant was largely abandoned, only to be revived upon the discovery of the universe's accelerating expansion. Under the cosmological constant model, dark energy does not change. It remains constant as the universe expands. This simplicity makes it an attractive explanation, as it provides a straightforward way to account for the observed acceleration in cosmic expansion. In this scenario, as space expands, the energy density of dark energy contributes increasingly to the overall dynamics of the universe, leading to continued acceleration. However, alternative theories suggest that dark energy could indeed vary over time. One such idea is quintessence, which posits a dynamic field with an energy density that changes according to the state of the universe. In this model, dark energy would exhibit different properties at various stages of cosmic history, potentially influencing the rate of expansion and even allowing for some interaction with matter. This variability adds complexity, but could help explain certain observations that remain unexplained by the cosmological constant theory. Current observations and data collection, such as galaxy clustering surveys and measurements of the cosmic microwave background radiation, are crucial in determining the true nature of dark energy. As cosmologists continue to refine their models and gather new insights, clarity regarding whether dark energy is constant or dynamic could significantly enhance our understanding of the evolution and ultimate fate of the universe. Ultimately, unraveling the mysteries of dark energy may provide fundamental insights into the underlying structure of the cosmos. Yes, there are several alternative theories and models that attempt to explain galaxy rotation curves without invoking dark matter. The compelling evidence for dark matter arises from the observation that stars at the outer regions of galaxies rotate at speeds that cannot be accounted for by the visible mass alone. Various alternatives seek to explain these phenomena through different mechanisms. One notable alternative is modified Newtonian dynamics, MOND, proposed by physicist Mordechai Milgrom in the early 1980s. This theory modifies Newton's laws of gravity to account for the observed rotation curves of galaxies. According to MOND, at very low accelerations, such as those found at the edges of galaxies, gravity behaves differently than what Newton's laws predict. By altering the equations governing gravity, MOND can replicate the flat rotation curves seen in galaxies without needing additional unseen mass. While MOND has been successful in some observational cases, it struggles with broader applications, such as explaining the dynamics of galaxy clusters or the cosmic microwave background. Another alternative involves the concept of self-interacting dark matter. While this still includes dark matter in the equation, it proposes that the interactions among dark matter particles could reduce the need for large amounts of unseen mass to explain rotation curves. If dark matter particles collide with each other, this could lead to different dynamics, for example, generating enough friction to alter the expected paths of stars within galaxies. Researchers are investigating whether self-interacting dark matter could bridge the gap between the need for dark matter and the observed properties of galaxies. Other theories include modified gravity models, such as Tevis or fifth force theories, which suggest the existence of additional forces at play. These concepts often seek to refine our understanding of how gravity operates on cosmic scales without requiring dark matter. While these alternative explanations present intriguing possibilities and merit investigation, the substantial evidence supporting dark matter, including observations of gravitational lensing and cosmic structure formation, has kept it at the forefront of cosmological theories. The discourse on these alternatives continues as researchers seek to reconcile observations with the fundamental physics of the universe. Dark energy is believed to be uniformly distributed throughout the universe, unlike ordinary matter, which clumps together to form stars, galaxies, and other structures. This uniform distribution implies that dark energy does not aggregate in the same way that visible matter does. Rather, it exerts a consistent but subtle influence on the fabric of space-time across vast distances. As the universe expands, the volume of space increases, and dark energy is theorized to exist as a constant energy density that fills this expanding space. This means that as new space is created through the expansion, an equivalent amount of dark energy is also added in. In this framework, the overall energy density of dark energy remains constant even as the universe grows. This characteristic is one reason why dark energy is a compelling explanation for the accelerating expansion of the universe, as its effects become more pronounced over larger scales. Some models propose that dark energy might not be as constant as traditionally thought. For instance, in theories like quintessence, the energy density of dark energy can vary with time and spatial location. Such models suggest that dark energy could change over the course of cosmic evolution, potentially leading to different behaviors in the expansion rate of the universe at various epochs. However, these variations must still be compatible with existing observational data, which currently supports the idea of a relatively constant distribution of dark energy. Ultimately, while dark energy appears to be uniformly spread throughout the cosmos, its exact nature and properties remain active areas of research. Ongoing studies aim to refine our understanding of how dark energy behaves and its role in the universe's future. As observations improve and new data emerges, we may gain greater insights into the subtleties of dark energy's distribution and its impact on cosmic expansion and structure formation. The search for dark matter extends beyond Earth-based experiments and into space. Satellites and space-based observatories play a crucial role in mapping the distribution of dark matter across the cosmos. By studying the gravitational effects on light from distant galaxies, scientists can create detailed maps of dark matter concentrations. These cosmic maps reveal a web-like structure, with dark matter forming the scaffolding upon which visible matter congregates. Understanding this large-scale structure is vital for comprehending how the universe evolved and how galaxies formed. The interplay between dark matter and ordinary matter in galaxy formation is a topic of intense study. Computer simulations suggest that dark matter halos form first, creating gravitational wells into which normal matter falls. This process leads to the formation of stars and galaxies within these dark matter cocoons. However, discrepancies between simulations and observations, such as the cuspy halo problem and the missing satellite problem, continue to challenge our understanding of dark matter's role in galactic evolution. Resolving these issues could provide crucial insights into the nature of dark matter and its interactions. Dark energy's influence extends beyond just accelerating the universe's expansion. It also affects the growth of cosmic structures. As the universe expands more rapidly due to dark energy, it becomes increasingly difficult for gravity to pull matter together to form new galaxies and clusters. This means that in the far future, as dark energy's effects become more dominant, the formation of new cosmic structures may slow down or cease entirely. Understanding this process is crucial for predicting the long-term evolution of the universe and its ultimate fate. The quest to understand dark energy has led to the development of new observational techniques and ambitious projects. One such endeavor is the study of baryon acoustic oscillations, BAO, which are periodic fluctuations in the density of visible matter in the universe. By measuring these oscillations at different cosmic epochs, scientists can track how the universe's expansion rate has changed over time, providing valuable data on dark energy properties. Future missions and telescopes are being designed specifically to study BAO and other dark energy-related phenomena with unprecedented precision. The potential connection between dark matter and dark energy remains an intriguing area of research. While currently treated as separate phenomena, some theories propose a link between the two. These unified dark fluid models suggest that dark matter and dark energy might be different aspects of the same underlying substance. While speculative, such theories highlight the possibility of a deeper connection between these mysterious components of the universe. Exploring these potential links could lead to a more comprehensive understanding of the cosmos and possibly reveal new fundamental physics. The implications of dark matter and dark energy extend beyond astrophysics and cosmology, influencing our understanding of particle physics and the nature of space-time itself. The search for dark matter particles has led to advancements in detector technology and pushed the boundaries of our understanding of particle interactions. Similarly, investigations into dark energy challenge our concepts of vacuum energy and the fundamental properties of space. These pursuits may ultimately lead to a revolution in physics, potentially unifying our understanding of the very large cosmology and the very small quantum mechanics. As our knowledge of dark matter and dark energy evolves, so too does our appreciation of the universe's complexity. These enigmatic components remind us that the cosmos is far stranger and more mysterious than we once imagined. They challenge our assumptions and drive us to explore new realms of physics and astronomy. As research continues, each new discovery not only brings us closer to understanding these phenomena, but also often raises new questions, ensuring that the pursuit of knowledge in this field remains dynamic and exciting. The center of a black hole, often referred to as the singularity, is a region where the gravitational pull becomes so intense that the laws of physics, as we currently understand them, break down. At this point, matter is thought to collapse into an infinitely dense state, and space-time curvature becomes extreme. The singularity is hidden from the outside universe by the event horizon, the boundary beyond which nothing, not even light, can escape. Within this central core, all known physical theories, including general relativity, struggle to provide satisfactory answers. General relativity posits that gravitational forces can significantly warp space-time, and this warping intensifies as one approaches the singularity. The conventional laws governing particles and forces cease to operate in ways we can measure or predict. The consequence of this breakdown presents a significant challenge for physicists, as reconciling general relativity with quantum mechanics remains one of the most important unresolved issues in modern theoretical physics. In the context of a black hole, particularly a rotating one known as a Kerr black hole, the singularity may take on a ring-like shape rather than a point. This configuration, combined with the extreme warping of space-time, complicates our understanding of what occurs in this region. Additionally, the presence of other phenomena, such as Hawking radiation, theorized by physicist Stephen Hawking, suggests that black holes can slowly evaporate over time, leading to questions about the fate of information that falls into a black hole. Further exploration into understanding what happens at the center of a black hole may require new physics that unites general relativity with quantum mechanics, often referred to as quantum gravity. As researchers continue to investigate the mysteries of singularities, revelations about their nature may not only reshape our understanding of black holes, but could also provide deeper insights into the fundamental workings of the universe itself. The question of whether information is destroyed in a black hole is a profound and contentious topic in theoretical physics, sparking considerable debate over the nature of black holes and the fundamental principles of quantum mechanics. According to classical interpretations of black hole physics, once matter and information cross the event horizon, they seem to be lost to the outside universe, leading to a scenario often referred to as information loss. This idea raises serious implications for the conservation of information, which is a cornerstone of quantum mechanics. This dilemma gained significant attention with Stephen Hawking's discovery of black hole radiation, which suggests that black holes can emit radiation and gradually lose mass over time. If a black hole could completely evaporate due to Hawking radiation, then any information about the matter that fell into it would appear to vanish as well. This notion created what is now known as the black hole information paradox, which challenges the principles of quantum mechanics that assert information cannot be destroyed. In the years since, various proposals have emerged to resolve this paradox. One prominent idea suggests that information is not lost, but rather encoded in the Hawking radiation itself. According to this perspective, while the information may seem to be inaccessible once inside the black hole, it could eventually be released as the black hole evaporates. In this way, the total information remains preserved, even if it takes a vastly complex form. Researchers like Juan Meldicena have explored holographic principles, indicating that information about the internal states of a black hole may be retained on its event horizon. Another development in this discourse is the idea of black hole complementarity, which posits that observers falling into a black hole and those outside the event horizon may have different descriptions of physical processes, yet these descriptions are equally valid. This concept suggests a deeper structure to space-time and emphasizes our incomplete understanding of black hole physics. As ongoing research, including advancements in quantum gravity and string theory, progresses, the question of information conservation remains a high priority in theoretical physics. Ultimately, resolving whether information is destroyed in a black hole could lead to monumental shifts in our understanding of fundamental laws governing the universe. Supermassive black holes are found at the centers of most galaxies, including our own Milky Way, where their masses can reach millions or even billions of times that of our Sun. The exact process of how these colossal entities form is still an area of active research, but several leading theories provide insight into their origins. One widely accepted idea suggests that supermassive black holes form through the gradual accumulation of matter over time. This process likely begins with the collapse of massive gas clouds early in the universe's history, leading to the formation of smaller black holes. These initial black holes can then grow by accreting matter from their surroundings or by merging with other black holes. This slow accumulation of mass over cosmic timescales could explain the enormous sizes of supermassive black holes observed today. Another possibility is that supermassive black holes might form directly from the collapse of extremely dense gas clouds or from the merger of smaller black holes in the early universe. There is also speculation that these black holes could be relics from the formation of the universe itself, formed in the high-density environment of the early cosmos. Some theories suggest that primordial black holes, which might have formed during the Big Bang, could have eventually grown into supermassive black holes. These ideas point to the complexity of black hole formation and highlight the ongoing efforts to understand the early stages of galaxy and black hole evolution. Recent observations show that supermassive black holes play a crucial role in shaping the galaxies that host them. Their immense gravitational pull can influence the motion of stars and gas in the surrounding region, affecting the overall structure of the galaxy. Supermassive black holes may also regulate star formation by heating up the surrounding gas or generating intense jets of particles that can suppress the collapse of gas into new stars. This feedback mechanism is thought to be important in maintaining a balance between the growth of galaxies and the formation of new stars. Understanding the formation and evolution of supermassive black holes is key to unlocking the mysteries of galaxy formation and evolution. Their discovery also raises new questions about the interplay between these cosmic giants and the galaxies they inhabit, offering clues about the fundamental processes that shape the universe. Would you like to dive deeper into any specific area, or would you prefer an engaging way to present these concepts in your channel content? When black holes finally approach very close proximity, they enter a phase known as the merger. During this event, a dramatic burst of gravitational waves is released, which can be detected by instruments like LIGO and Virgo. This merger event signals the transformation of two separate black holes into a single, more massive black hole. During the final moments, massive amounts of energy are released, and the characteristics of the resulting black hole can vary based on the initial spins and masses of the original black holes. The aftermath of the merger contributes to the growth of supermassive black holes at the centers of galaxies and informs models of galaxy evolution. In addition, these binary systems are crucial for understanding the nature of gravity and the fabric of space-time itself. With advancements in technologies to detect gravitational waves, our understanding of binary black hole evolution continues to evolve, revealing the intricacies of some of the universe's most powerful phenomena. The final moments of a black hole's evaporation, a process predicted by the theory of Hawking radiation, are among the most enigmatic and thought-provoking phenomena in modern physics. Over astronomical timescales, black holes lose mass by emitting particles through quantum effects near their event horizons. This slow radiation results from the virtual particles that constantly pop in and out of existence in the vacuum of space. As a black hole evaporates, it goes through a gradual decline in mass, but during the final moments, something extraordinary occurs. The rate of emission of Hawking radiation increases dramatically, leading to a rapid decrease in mass. As it shrinks, the black hole becomes hotter, and its emitted radiation becomes more intense. This last phase is often conceptualized as a sort of cosmic explosion, as the energy density reaches extraordinary levels just before the black hole dissipates completely. During this climactic stage, the black hole may emit bursts of high-energy particles, including photons and other fundamental particles. This final outpouring could potentially release an enormous amount of energy, whispering away the last remnants of the black hole into the surrounding space. If this particle emission were to occur within a stellar environment, it might provide insights into how stellar remnants interact with their surroundings during this transformative phase. Importantly, the information paradox arises in these final moments, questioning whether the information about the matter that fell into the black hole is destroyed or retains some form of accessibility after evaporation. This paradox remains one of the open questions in theoretical physics, captivating researchers and driving investigations into the fundamental nature of information in the universe. As scientists continue to study black holes and their evaporation, we may gain deeper insights into the realms of quantum mechanics and the fabric of space-time itself. The true shape of the universe is one of the most profound questions in cosmology, and it closely relates to the underlying geometry of space-time itself. The current understanding suggests that the universe can be described using different geometrical models that depend on the average density of matter and energy it contains. One possible shape is flat, resembling a sheet of paper. In a flat universe, parallel lines would never meet, and the overall geometry would follow the rules of Euclidean geometry. Observations, particularly those from the cosmic microwave background radiation, indicate that the universe appears very close to flat on a cosmic scale, suggesting that the total density of matter and energy is nearly equal to the critical density needed to achieve this geometry. Another scenario proposes a closed universe, akin to the surface of a sphere. In this model, the universe would be finite but unbounded. If you were to travel in a straight line in a closed universe, you would eventually return to your starting point. The curvature of space would mean that geometric rules diverge from our familiar Euclidean intuitions, leading to phenomena like the potential for a big crunch, where the universe might eventually collapse back on itself. Conversely, an open universe resembles a saddle shape, where parallel lines would eventually diverge. This model implies that the universe could expand indefinitely without returning to a previous configuration. Each model has distinctive implications for the ultimate fate of the universe and the behavior of light and objects within it. In addition to these classical models, the universe's shape can be influenced by dark energy, a mysterious force driving its accelerated expansion. Understanding the true shape of the universe remains an active area of research, with ongoing observations and studies seeking to refine these models. As we delve deeper into the cosmos and gather more data, scientists continue to piece together the intricate puzzle of our universe's structure and its cosmic destiny. Yes, there are indeed structures in the universe that exceed the scale of galaxy superclusters, which are already vast collections of galaxies held together by gravity. One of the largest known structures is called a cosmic filament, which is a part of the large-scale structure of the universe. These filaments consist of immense threads of galaxies and dark matter, forming a vast web-like structure that spans hundreds of millions of light years across. The largest of these structures are often referred to as superclusters of superclusters. An example is the Laniakea supercluster, which contains the Milky Way and is itself a part of an even larger network of galaxy clusters and filaments. Within this web, clusters and superclusters group together in a way that indicates the complex gravitational influences at play across cosmic scales. Beyond cosmic filaments, there are also structures called voids. Voids are enormous, relatively empty regions of space surrounded by filaments and clusters of galaxies. These voids can stretch for hundreds of millions of light years and represent some of the largest unoccupied areas in the universe. The interplay of dense regions filled with galaxy clusters and these vast voids helps to shape the overall structure of the cosmos. As astronomers employ advanced observational technologies, they continue to uncover the complexity and scale of the universe's architecture. The hierarchical nature of cosmic structures, from galaxies to superclusters and beyond, paints a fascinating picture of how gravity and dark matter have sculpted the universe over billions of years. Each discovery furthers our understanding of the universe's large-scale structure and the underlying forces at play. The formation of the first galaxies is a key event in cosmology, occurring roughly at the end of the cosmic dark ages, around billions of years after the Big Bang. During this time, the universe was cooling and expanding, creating conditions conducive to the formation of matter. The initial moment saw a uniform expanse of gas, primarily composed of hydrogen and helium, but gravitational instabilities began to disrupt this uniformity. As tiny fluctuations in density occurred, regions with slightly more matter began to attract additional gas. Over time, these regions collapsed under their own gravity, leading to the creation of the first star clusters. These primordial stars were likely massive and short-lived, burning brightly before exploding as supernovae. The explosion enriched their surroundings with heavier elements, facilitating the formation of subsequent generations of stars and eventually galaxies. The process of galaxy formation was not uniform. Some regions experienced rapid star formation, leading to the creation of small galaxies that merged over time. This merging process allowed for the buildup of larger and more complex structures. The role of dark matter is crucial here, as it provides the gravitational scaffolding necessary to capture and hold regular matter, influencing how galaxies clustered together. As these early galaxies continued to evolve, they began to establish the framework for the galaxies we observe today. Their behavior shapes the large-scale structures of the universe and influences the formation of the cosmic web we see in the present. Understanding how these first galaxies formed and evolved is fundamental to unraveling the history of the universe and our place within it, making it an essential area of inquiry for astronomers and cosmologists alike. The filamentary structure of the cosmic web arises from gravitational interactions on a vast scale, shaping the distribution of galaxies, galaxy clusters, and dark matter throughout the universe. This intricate arrangement is a result of the fundamental laws of gravity working over billions of years to create a vast network that interconnects all visible matter. In the early universe, matter was primarily distributed uniformly, but quantum fluctuations from the inflationary period created tiny density variations in the primordial gas. Over time, these small fluctuations intensified due to gravitational attraction, leading to the formation of regions with higher density. Galaxies and clusters began to form in these dense areas, while less dense regions expanded. This uneven distribution of matter eventually led to the emergence of a network of filaments and nodes. The filaments themselves are composed mainly of dark matter and are often surrounded by a hot gas. Dark matter, which makes up a significant portion of the universe's mass, does not emit light and remains invisible. Yet, it exerts a gravitational influence that guides the motion of visible matter. As galaxies and clusters drift through space, they tend to move toward these filamentary structures, which act as highways for cosmic matter, drawing galaxies together through gravitational attraction. This web-like configuration creates a striking contrast with vast voids, which are expansive regions of space with comparatively few galaxies. The energy dynamics and gravitational influences within these filaments help explain the large-scale structure of the universe as we observe it today. Ongoing research, including simulations and observations, continues to enhance our understanding of how these cosmic webs form and evolve, revealing the underlying forces that shape the universe on the grandest scales. Voids in the universe are vast, relatively empty regions containing far fewer galaxies than typical areas of space. Their existence is deeply rooted in the mechanics of cosmic evolution and the gravitational dynamics that shape the large-scale structure of the universe. Understanding why these voids form involves investigating the fundamental processes that govern the distribution of matter and energy. At the earliest stages of the universe, matter was distributed relatively uniformly, influenced by quantum fluctuations. As the universe expanded and cooled, gravity began to play a significant role. Small density variations led to regions of space where matter started to clump together, forming galaxies and galaxy clusters. However, in areas where the density was lower, the gravitational pull was insufficient to attract significant amounts of matter, resulting in regions that remained largely empty. These empty spaces eventually became the voids we observe. Over time, as galaxies formed and evolved, the interactions within dense regions like clusters and filaments caused them to grow in size. Voids are typically surrounded by cosmic filaments, the vast highways of galaxies and dark matter that stretch across the universe. The expansion of the universe further contributes to the growth of these voids as the distance between galaxy clusters increases. These voids, while seemingly empty, play a critical role in the evolution of the universe. They provide a contrasting environment to the crowded, cluster-rich regions and help to define the overall structure of the cosmos. Today, scientists continue to study voids using advanced observational techniques and simulations to understand their formation and impact on the universe's large-scale evolution. Through these investigations, astronomers hope to answer questions about the nature of dark energy, cosmic expansion, and the overall geometry of the universe. The study of cosmic voids and the voids in our own galaxy offers fascinating insights into the workings of the universe. These vast expanses of empty space are found throughout the cosmos and have a significant impact on the overall structure of the universe. The biggest voids, known as supervoids, can span hundreds of millions of light years across and are almost completely devoid of galaxies. Some of the largest known supervoids are the Eridanus supervoid and the Boötes void, both of which are surrounded by dense filaments of galaxies. These supervoids are thought to have formed in the early universe, when quantum fluctuations and gravity began to shape the distribution of matter. Although these voids are seemingly empty, they are not completely devoid of activity. For example, cosmic rays and dark energy interact with these regions, and scientists are working to understand how these factors contribute to the evolution of the universe. Additionally, the study of voids in our galaxy, such as a local void, can help us understand the formation of our Milky Way and its relationship with other nearby galaxies. As we continue to map the universe and identify more voids, we gain a deeper understanding of how matter and energy have distributed themselves across the cosmos, shedding light on the mysterious forces shaping the very fabric of space-time itself. How common Earth-like planets are in the universe has gained significant momentum in recent years, particularly with advancements in observational technology and space missions such as the Kepler Space Telescope. Estimates suggest that Earth-like planets, which are defined by their similar size, composition, and distance from their stars, could be relatively common across the vast cosmos. Research indicates that potentially habitable planets are often found within what's known as the habitable zone of their stars. This is a region where conditions might allow liquid water to exist on a planet's surface, a crucial factor for life as we know it. Studies have demonstrated that many stars possess multiple planets, and a significant fraction of those can reside within this habitable zone. Some estimates propose that as many as 1 in 5 stars could host an Earth-sized planet in their habitable zone. Additionally, binaries may impact the types of planets that emerge. For instance, gas giants and icy bodies may form at different distances from the stars than they would in a solitary star system. The gravitational influence of the stars can also lead to the possibility of capturing planets that form further out or remnants of disrupted bodies, broadening the diversity of planetary types. Lastly, the orbits of planets in binary systems can be notably more complex. Some planets may possess stable orbits akin to those in a single star system, while others might have eccentric orbits or face instability due to the gravitational interplay of the two stars. This variety results in a diverse range of potential planetary systems, allowing for a broader exploration of conditions under which planets can form. A key area of inquiry for understanding the potential for life in the universe involves determining the upper size limit for a habitable planet. This involves assessing various factors that influence conditions necessary for life as we know it. Generally, habitable planets are those that fall within a range where liquid water can exist on their surfaces, often referred to as Earth-like planets. However, as planet size increases, several key factors come into play that may limit habitability. One primary consideration is gravity. Larger planets tend to have stronger gravitational fields, which can retain thicker atmospheres composed of various gases. While a substantial atmosphere is essential for insulating a planet and providing pressure, if the planet becomes too large, often categorized as a super-Earth, its atmosphere could also become dominated by gases like hydrogen and helium, forming a gas giant. This transition tends to limit the potential for land and liquid water on the surface, conditions that are generally required for life. Another critical aspect is the planet's geological activity. Larger terrestrial bodies are likely to have more significant internal heat, which can promote geological processes such as plate tectonics and volcanic activity. While these processes can be beneficial for creating diverse climates and ecosystems, they could also lead to extreme conditions that may be challenging for life. If a planet size leads to excessive heating, it might create an inhospitable environment characterized by high pressures or temperatures. The balance of these factors suggests that while planets larger than Earth, up to about 2 to 3 times its size, may still maintain habitable conditions, as they continue to grow in size, the likelihood of retaining an Earth-like environment expands. Consequently, the concept of a habitable zone is intricately tied to both the planet's size and its corresponding geological and atmospheric characteristics. As research progresses and we discover more exoplanets, our understanding will evolve, potentially revealing surprising limits on habitability. Then, the potential diversity of alien biochemistries is both mind-boggling and fascinating. Life on Earth is primarily carbon-based, utilizing water as a solvent, and relies on a combination of amino acids, nucleic acids, and lipids to create its complex biological structures. However, when we venture beyond our planet, the imagination runs wild with the possibilities of life forms that might exist under entirely different conditions. For instance, scientists speculate about the potential for silicon-based life. Silicon shares many chemical properties with carbon, so it could theoretically form the backbone of complex molecules. Such life forms might inhabit environments rich in high temperatures, such as near volcanic activity, or even on certain planets and moons in our solar system that harbor extreme conditions. Beyond the molecular structure of life, the conditions required for survival could lead to a vast array of biochemical processes. For example, while Earth life thrives on oxygen to power cellular respiration, alien organisms might use other elements like sulfur or methane in their energy-producing pathways. This could lead to life existing in places previously deemed inhospitable, such as the thick clouds of Venus or the icy surfaces of Europa and Enceladus, where subsurface oceans may harbor unseen life. Moreover, the genetic systems of extraterrestrial organisms could vary significantly from our own. They might use alternative nucleic acids instead of the familiar DNA and RNA, or utilize entirely new methods of information storage and transfer. Exploring these possibilities expands our understanding of what life could be and challenges our definitions of biology, leading us to reconsider how life might exist in myriad and unimaginable forms throughout the universe. In a methane-based ecosystem, life would evolve in environments vastly different from those we know on Earth. One prominent candidate for such ecosystems is Titan, Saturn's largest moon, where methane and ethane exist in liquid form and create vast lakes and rivers. Life forms adapting to this unique setting would likely develop biochemistries that work efficiently in frigid temperatures, as Titan's surface is around minus 180 degrees Celsius. Organisms in a methane-based environment might utilize methane as a primary energy source instead of oxygen. Instead of relying on photosynthesis, life could adopt chemosynthesis, creating energy through chemical reactions involving methane and hydrogen. These hypothetical organisms might develop specialized cell structures or membranes that can withstand the low temperatures and high viscosity of liquid methane, potentially resembling extremophiles found on Earth that thrive in similarly harsh conditions. The appearance and morphology of such methane-based life forms might diverge significantly from terrestrial organisms. For instance, rather than the familiar green plants, we could expect to see organisms with different pigmentation or even transparent features that help them thrive in the dim light of distant stars or the thick atmosphere of Titan. Their structures might be more robust, with rigid bodies capable of stabilizing themselves in liquid methane, potentially resembling jellyfish or even bizarre crystalline formations that can absorb and utilize available energy sources uniquely. Furthermore, metabolism in such organisms might involve unique biochemical pathways, possibly resulting in a very different form of cellular organization. The absence of water as a solvent could mean life would not depend on amino acids in the same way we do. Instead, alternative molecules might play crucial roles in the structure and function of life, offering a glimpse into forms of biology that stretch our imagination and challenge our understanding of life's possibilities. Detecting biosignatures on distant exoplanets is one of the most exciting frontiers in modern astronomy. Scientists are focused on identifying chemical markers in the atmospheres of exoplanets that could indicate the presence of life. These biosignatures can take many forms, often involving the detection of certain gases that are typically produced by biological processes. For instance, the simultaneous presence of oxygen and methane in an atmosphere could hint at biological activity, as these gases tend to react with one another and would require a constant replenishing source, which life could provide. One of the most powerful tools at our disposal is the transit method, which involves monitoring the light from a star as a planet passes in front of it. During this transit, a small amount of starlight filters through the planet's atmosphere, allowing scientists to analyze the spectrum of light. This spectral data reveals the chemical composition of the atmosphere. By identifying specific absorption lines, researchers can determine the presence of potential biosignature gases. Additionally, future missions are planning to utilize space telescopes equipped with advanced spectrographs that can observe smaller and cooler exoplanets within their stars' habitable zones. The James Webb Space Telescope, for example, is expected to greatly enhance our ability to study exoplanet atmospheres and detect potential biosignatures. These instruments will enable scientists to look for gases such as oxygen, ozone, methane, carbon dioxide, and others that, when found together, might suggest biological processes are at work. In the universe, star formation in extreme environments like the centers of galaxies presents a fascinating challenge due to the intense conditions present in these regions. The core of a galaxy, especially in those with active supermassive black holes, is characterized by high radiation levels, gravitational forces, and significant turbulence. Despite these extreme factors, stars still manage to form, albeit through different mechanisms than in quieter regions of space. In galactic centers, one crucial aspect of star formation is the presence of massive amounts of gas and dust, which gather into dense molecular clouds. These clouds are often subjected to turbulent conditions created by the gravitational pull of the supermassive black hole and the energetic activity surrounding it. Interestingly, while the intense environment could disrupt star formation, it also leads to the compression of gas, which plays a vital role in the process. As the gas clouds become denser, they can undergo gravitational collapse, eventually forming new stars. The presence of high-energy radiation from accreting matter around supermassive black holes can lead to heating and ionization within these dense clouds. Yet, certain regions of the clouds can shield themselves from this radiation. This allows parts of the molecular clouds to maintain their cool temperatures, enabling the process of star formation to continue. Additionally, interactions between gas clouds can trigger shock waves, further compressing the material and sparking the formation of new stars. In such extreme environments, star formation may occur more rapidly, leading to the creation of massive stars. These stars evolve quickly and can end their lives in spectacular supernova explosions, which then enrich surrounding regions with heavier elements, promoting further star formation. This cyclic process contributes to the dynamic evolution of the galaxy over time, illustrating how, even in the most hostile conditions, the universe has a remarkable ability to create and nurture new stars. Ultra-high-energy cosmic rays are among the most mysterious and energetic particles in the universe, with energies exceeding 1 billion gigaelectron volts, which is significantly higher than any produced in human-made particle accelerators. Understanding their origin has puzzled scientists for decades, leading to various theories regarding their sources, which are primarily linked to some of the most energetic astrophysical phenomena known. One leading candidate for the origin of ultra-high-energy cosmic rays is supernova remnants. When massive stars explode, they release tremendous amounts of energy, creating shock waves that can accelerate particles to extraordinarily high energies. These shock waves interact with surrounding gas and magnetic fields, providing the necessary conditions for particles, primarily protons, to gain energy and escape the remnants of the explosion. While this process is a viable source, it may not account for all the highest energy cosmic rays detected. Another strong contender is active galactic nuclei, particularly those associated with supermassive black holes at the centers of galaxies. As matter spirals into these black holes, it releases immense amounts of energy in the form of jets, which can accelerate particles to ultra-high energies. The conditions surrounding these massive black holes, including their powerful magnetic fields and turbulent environments, serve as ideal environments for cosmic ray acceleration. Gamma-ray bursts, which are extremely energetic explosions associated with the collapse of massive stars and mergers of compact objects, have also been proposed as potential sources. The immense energy released during these events can accelerate particles to incredibly high energies. However, determining the exact mechanisms and locations of particle acceleration in these extreme environments remains a significant area of research. Despite advances in observational techniques, the precise origins of ultra-high-energy cosmic rays remain elusive. Ongoing studies utilizing observatories around the world aim to establish connections between detected cosmic rays and their potential sources, helping to unveil the intricacies of these energetic particles and improve our understanding of the universe's most powerful phenomena. Binary star systems consist of two stars orbiting around a common center of mass, and the exchange of mass between these stars is a fascinating process that can significantly influence their evolution. Mass transfer occurs when one star evolves and exhausts its nuclear fuel, often expanding into a larger, more volatile state, such as a red giant. This expansion can lead to various outcomes depending on the specific characteristics of the binary system. As one star in the binary system expands, its outer layers may spill over into the gravitational pull of its companion star. This process is often facilitated by the presence of an accretion disk, which forms around the receiving star as it pulls a material from its neighbor. The accretion disk acts as a funnel, allowing material to spiral down onto the surface of the companion star. The efficiency of this mass transfer depends on factors such as the distance between the stars and the rate at which the donor star expands. There are different regimes of mass transfer, with the two primary types being stable and unstable mass transfer. In stable mass transfer, the process occurs slowly and steadily, allowing the receiving star to adjust gradually to the increased mass, often leading to long-term changes in brightness and composition. In contrast, unstable mass transfer can lead to rapid and dramatic exchanges, resulting in significant effects such as nova eruptions, where the accreted material undergoes explosive thermonuclear reactions on the surface of the receiving star. Mass transfer can drastically alter the evolution of both stars in a binary system. For instance, the gaining star might undergo changes that lead to the formation of a white dwarf or even a neutron star or black hole, depending on the amount of mass it receives and its original mass. This complex interplay of mass exchange ultimately shapes the life cycles of stars and can lead to spectacular cosmic events like Type Ia supernovae, providing essential insights into stellar evolution and the dynamics of binary star systems. In the core of a red supergiant star, a dramatic series of processes unfolds just before the star collapses after exhausting its nuclear fuel for fusion reactions. The red supergiant has progressed through multiple stages in which it burns increasingly heavier elements. Initially, hydrogen is fused into helium, then helium into carbon and oxygen, and this continues until iron accumulates in the core. As the core builds up iron, an essential transformation occurs. Iron is unique in that fusing it does not produce energy. Instead, it consumes energy. This results in a halt in the star's ability to generate the outward pressure needed to counteract the immense gravitational forces pulling the core inward. Without that pressure, the balance that has sustained the star for millions of years begins to deteriorate, leading to further instability. With the core unable to support itself, the gravitational forces cause it to collapse rapidly. This collapse occurs at remarkable speed, leading to an increase in density and temperature. As the core becomes denser, conditions can rise to extremely high temperatures of around several billion degrees. This creates a situation where photodisintegration occurs, as energetic photons can break apart iron nuclei, generating a variety of lighter particles such as protons and neutrons within the core. The final moments are marked by a buildup of energy from the core's collapse and the subsequent rebound effect from the outer layers of the star. Once the core collapses to a critical point, which is typically around 3 solar masses, it will transform into a neutron star or possibly a black hole, depending on the mass. This crash culminates in a supernova explosion, unleashing extraordinary amounts of energy and ejecting the outer layers of the star into space. This magnificent event not only marks the end of the red supergiant, but also plays a crucial role in the cosmic recycling of elements, enriching the interstellar medium and paving the way for future star formation. Music. Reconciling quantum mechanics with general relativity is one of the most profound challenges in modern theoretical physics. These two pillars of our understanding of the universe operate very successfully within their own domains, but are fundamentally incompatible when attempting to apply them simultaneously in extreme environments, such as near black holes or during the moments after the Big Bang. Quantum mechanics describes the behavior of particles at very small scales, where probabilities and uncertainties play key roles. On the other hand, general relativity, formulated by Albert Einstein, describes the gravitational force as the curvature of space-time caused by mass and energy operating on a much larger scale. When scientists try to apply quantum principles to gravitational fields, several fundamental issues arise, particularly related to the concept of space-time itself, which general relativity treats as a smooth continuum, whereas quantum mechanics suggests a discrete nature at the Planck scale. One approach to reconciling these theories is through the development of a quantum theory of gravity. This is still an active area of research, with several theoretical frameworks being explored. One prominent candidate is string theory, which posits that fundamental particles are not point-like objects, but rather tiny, vibrating strings. String theory suggests that these strings exist in higher dimensions, thereby providing a structure that could unify all fundamental forces, including gravity, within a single theoretical framework. Another approach is loop quantum gravity, which seeks to quantize space-time itself. This theory proposes that space-time is made up of discrete units, like a fabric woven from loops. By applying quantum principles to the geometry of space-time, loop quantum gravity aims to create a coherent picture that includes both quantum effects and gravitational interactions. While promising, each of these theories still faces significant challenges, including testing their predictions through experiments and observations. Scientists continue to explore ways to bridge the two realms, focusing on understanding phenomena like black hole evaporation, the early universe, and potential observational consequences. Although a complete reconciliation remains elusive, ongoing efforts highlight the quest to deepen our understanding of the universe at its most fundamental levels. Quantum entanglement is one of the most intriguing phenomena in quantum mechanics, reflecting a deep connection between particles that often defies our classical understanding of the universe. When two or more particles become entangled, their quantum states become linked in such a way that the state of one particle cannot be fully described without considering the state of the other, no matter how far apart they are. This relationship persists even when the entangled particles are separated by vast distances, a feature that Albert Einstein famously referred to as spooky action at a distance. The true nature of entanglement lies in the principles of superposition and non-locality. When particles are entangled, they exist in a state of superposition, where each particle is not in a definite state, but rather in multiple potential states simultaneously. Upon measurement of one particle, its state collapses to a definite value, and this instantaneously determines the state of the other particle. This instantaneous correlation raises profound questions about the nature of information and causality in quantum mechanics. Entanglement challenges our understanding of reality, prompting discussions about whether classical intuitions about separability and locality hold true in the quantum realm. Experimental tests of Bell's theorem have shown that entangled particles exhibit correlations stronger than those allowed by classical physics, confirming that nature operates according to quantum rules that are fundamentally different from those we experience in everyday life. The implications of quantum entanglement extend beyond theoretical physics. They have practical applications in emerging fields like quantum computing and quantum cryptography. By harnessing entangled states, researchers are developing technologies that exploit these unique properties for unprecedented computational power and secure communication techniques. Ultimately, while quantum entanglement continues to puzzle and inspire scientists, it stands as a testament to the complexity and interconnectedness of the universe at the quantum level, inviting further exploration into the fundamental nature of reality itself. The question of whether space-time is quantized at the smallest scales is a central topic in theoretical physics, particularly in the quest to unify quantum mechanics and general relativity. Current understanding suggests that space-time, as described by general relativity, is a smooth continuum. However, when considering phenomena at extremely small scales, on the order of the Planck length, which is about 1.6 times 10 superscript 3m, traditional descriptions of space-time may break down. Several theoretical frameworks propose that space-time might indeed be quantized. Loop quantum gravity is one such approach, which suggests that space-time itself consists of discrete units, resembling a network made up of tiny loops. In this theory, the geometric properties of space-time are quantized, meaning that space and time could be represented as a collection of finite, indivisible elements. This model aims to reconcile the smooth geometry of general relativity with the discrete nature of quantum mechanics. String theory is another candidate that posits a fundamental description of matter and forces not in terms of point particles, but as one-dimensional strings vibrating at specific frequencies. These strings exist in higher dimensions, and the compactification of these dimensions could lead to a quantized structure of space-time. In string theory, the interactions and dynamics of strings could imply that space-time has a fundamental granular quality at very small scales. Despite these theories, the quantization of space-time is not yet established and remains a topic of active research, as no experimental evidence currently confirms the discrete nature of space-time, primarily because the scales involved are well beyond the reach of current technology. As scientists continue to explore the intersections of gravity and quantum mechanics, the question of whether space-time is fundamentally quantized may progressively yield insights, contributing to a deeper understanding of the universe's structure at its most fundamental levels. The universe, as we understand it, has three dimensions of space: length, width, and height, along with the dimension of time, forming what is commonly known as space-time. In this framework, events are described by four-dimensional coordinates, where three dimensions account for spatial positions, and the fourth dimension represents the progression of time. This four-dimensional model aligns well with both general relativity and our everyday experiences. However, many theoretical physicists propose that our universe may actually possess additional dimensions beyond the familiar four. String theory, for instance, suggests that fundamental particles are not point-like objects, but rather one-dimensional strings that vibrate in multiple dimensions. In its most popular formulations, string theory requires 10 or even 11 dimensions to be mathematically consistent. These extra dimensions are theorized to be compactified or curled up at such small scales that they remain undetectable in our everyday observations. The idea of extra dimensions provides intriguing possibilities for unifying the fundamental forces of nature. It allows for various mechanisms that could explain the gravitational force's relative weakness compared to other fundamental forces, as well as offering potential insights into the nature of dark matter and dark energy. However, direct evidence for these additional dimensions remains elusive. While some experiments, such as those conducted at particle colliders like the Large Hadron Collider, aim to probe high-energy phenomena that could hint at extra dimensions, the confirmation of their existence is still an open question. As research continues and our understanding of the fundamental structure of the universe evolves, the true nature of dimensions beyond the observable three spatial and one temporal may eventually become clearer, enriching our comprehension of reality itself. Exploration of the question of whether the laws of physics vary across the universe is a topic of significant interest and debate in modern cosmology and theoretical physics. Currently, the prevailing view among scientists is that the fundamental laws and constants of physics are uniform throughout the observable universe. This assumption is based on extensive empirical evidence and the success of the standard model of particle physics and general relativity, which accurately describe a wide range of phenomena across different cosmic scales. However, some theories and observations propose that the laws of physics may not be entirely constant. For instance, certain models in cosmology suggest that the laws might have been different in the early universe, particularly during events such as the Big Bang or phase transitions that occurred shortly afterward. In these scenarios, the fundamental constants might have taken on different values in the extreme conditions present during those times. Additionally, the concept of a multiverse posits the existence of multiple, perhaps infinite, universes, each potentially governed by different physical laws or constants. These universes might vary widely in their physical manifestations, leading to diverse forms of matter, forces, and possibly even life. While the multiverse theory is fascinating, it is still highly speculative and lacks direct empirical evidence to confirm its existence. In recent years, researchers have sought to investigate potential variations in fundamental constants over cosmic timescales. For instance, studies examining the light from distant quasars have looked for possible changes in the fine structure constant, a fundamental parameter related to electromagnetic interactions. While some findings have suggested slight variations, these results are controversial and subject to ongoing scrutiny. Another approach involves examining the possibility of spatial variations in physical laws. Some researchers have explored scenarios in which constants, such as the gravitational constant or the cosmological constant, might differ from one region of space to another. Such variations could arise in contexts that extend beyond our current understanding of physics. While the prevailing belief is that the fundamental laws of physics are consistent across the observable universe, there are intriguing avenues of research investigating the possibility of variations. These questions continue to inspire theoretical exploration and observational studies, pushing the boundaries of our understanding of the universe's underlying principles. As our knowledge of fundamental physics evolves, the possibility of discovering new insights into the uniformity or lack thereof of physical laws remains an exciting frontier in scientific inquiry. Beyond the observable universe lies a realm that is not accessible to observation and is largely unknown. Yet, It captures the imagination of scientists and cosmologists alike. The observable universe is defined by the region of space from which light has had time to reach us since the Big Bang, approximately 13.8 billion years ago. This means we can observe galaxies and cosmic events up to a distance of about 13.8 billion light years. However, space itself has been expanding since the Big Bang, meaning there are regions of the universe that are beyond our observational capabilities. One possibility for what lies beyond the observable universe is simply more of the same universe we can see. The universe is thought to be homogeneous and isotropic on large scales, suggesting that structures like galaxies, clusters, and voids are likely to continue beyond our current observational limits. The same physical laws and constants we observe should apply, leading to a vast extension of the universe that we can only infer. Another intriguing concept is the possibility of a flat or infinite universe. If the universe is indeed infinite, then beyond the observable universe, there would be an endless expanse of space that continues infinitely in all directions. Given this scenario, distant regions could harbor the same types of structures, stars, and galaxies seen within our observable limits. The multiverse theory proposes a different perspective on what exists beyond the observable universe. This theory suggests that our universe might be just one of many separate universes, each potentially governed by different physical laws or constants. In this framework, different pocket or bubble universes could exist with unique properties, including varying dimensions, forces, and even fundamental constants. The nature of these universes could be vastly different from our own, leading to different forms of matter, energy, and possibly even different types of physical processes. Moreover, the fabric of space-time itself may hold mysteries beyond the observable universe. Hypothetical concepts such as string theory and dimensions beyond the familiar three-dimensional space and one-dimensional time suggest that our understanding of reality could be expanded to include additional dimensions that are not directly observable. Ultimately, while we cannot directly observe what lies beyond the observable universe, theoretical explorations continue to drive our understanding of the cosmos. These ideas serve to remind us that the universe is vast and rich with possibilities, inviting scientists to engage in ongoing inquiry about the nature of existence itself and what mysteries might still remain to be unveiled. The prospect of observing the universe's first stars, often referred to as population 3 stars, is one of the intriguing challenges in modern astrophysics. These stars are thought to have formed from primordial gas, primarily composed of hydrogen and helium, shortly after the Big Bang, approximately 100 million to 400 million years after the event. Due to their unique characteristics, including likely being massive, short-lived, and composed almost entirely of the primordial elements, the first stars could provide essential insights into the early universe and the processes that led to the formation of galaxies and complex structures. Observing these ancient stars directly poses significant challenges. One of the primary issues is that they are located very far away, often at redshifts beyond 6, meaning the light we would need to observe them has been traveling for billions of years. As a result, the light from these stars is very faint and much dimmer than that of more contemporary stars, making detection with current telescopes difficult. However, advancements in technology and observational techniques offer hope for the future. Next-generation space telescopes, such as the James Webb Space Telescope, planned to launch in the coming years, are designed to observe the infrared wavelengths of light. These wavelengths allow astronomers to penetrate the dense clouds of dust and gas that can obscure observations in optical ranges. As these advanced instruments come online, they may be able to detect the faint signatures of the first stars, or the ionizing radiation from their formation, which played a critical role in the reionization of the universe. In addition to direct observations, astronomers are also exploring indirect methods to study the first stars. This includes examining the cosmic microwave background radiation, which provides clues about the conditions prevailing in the early universe. Simulations and models that mimic the formation and behavior of population 3 stars can also yield valuable insights into their characteristics and the impact they had on their environments. While the prospect of directly observing the universe's first stars remains a formidable challenge, ongoing advancements in technology and innovative observational strategies make it a tantalizing possibility for the future. The study of these primordial stars would deepen our understanding of the early universe, shedding light on the processes that led to the development of galaxies, stars, and the complex cosmic tapestry we see today. Probing the universe's dark ages is an essential aspect of understanding cosmic history, specifically the period following the Big Bang when the universe expanded and cooled, but before the first stars began to form. This epoch, roughly between 400,000 years and about 1 billion years after the Big Bang, is termed the Dark Ages because during this time the universe was devoid of bright sources of light, making it challenging to observe using traditional methods. One of the primary methods of probing this period is through the study of the cosmic microwave background radiation, or CMB. The CMB is the afterglow of the Big Bang, released when the universe cooled enough for electrons and protons to combine and form neutral hydrogen atoms. This event allowed photons to travel unimpeded through space, providing a snapshot of the universe when it was about 300,000 years old. By analyzing the CMB's temperature fluctuations and polarization patterns, scientists can gather information about the conditions during the universe's formative years, laying the groundwork for understanding the subsequent dark ages. Another critical approach is the exploration of high-redshift astronomical objects. As light from distant galaxies and quasars takes billions of years to reach us, observing these objects allows astronomers to peek back in time. By studying objects at redshifts greater than 6, scientists can infer conditions of the universe during the dark ages. The light emitted by early stars and galaxies can provide insights into when the first luminous sources emerged and how they affected their surroundings. One promising observational target is the detection of the first stars, known as population 3 stars, which are believed to have formed from primordial gas composed mainly of hydrogen and helium. Understanding the formation and impact of these stars will provide crucial information about the reionization epoch, the period when the universe transitioned from the Dark Ages to an ionized state filled with light. Upcoming observatories, such as the James Webb Space Telescope, are designed to probe this era by observing the infrared wavelengths that could reveal significant information about early stars and galaxies. Another technique involves searching for signatures left in the intergalactic medium during the Dark Ages, specifically through a process called 21 centimeters hydrogen mapping. This method takes advantage of the hyperfine transition of neutral hydrogen, which emits radiation at a frequency of 21 centimeters. By mapping variations in this signal on large scales, astronomers can glean insights into the density and temperature of the hydrogen gas filling the universe during the Dark Ages, revealing details about cosmic structure and the conditions leading to the first galactic formations. The combination of these observational and theoretical approaches helps create a more comprehensive understanding of the Dark Ages. As technology advances and new observational tools come into play, scientists continue to refine their models and expand our understanding of this enigmatic period in cosmic history. Ultimately, probing the universe's dark ages will illuminate many fundamental aspects of the universe's evolution and formation. The ultimate limits of astronomical observations are determined by a combination of physical, technical, and philosophical factors. As we strive to explore the cosmos, understanding these limits can help guide the development of new technologies and observational strategies. One of the primary physical limits arises from the finite speed of light. Because light takes time to travel across vast distances, astronomical observations are always effectively peering back in time. The farthest objects visible to us are those whose light has been traveling for billions of years, meaning we are observing them as they were in the distant past. In addition to the finite speed of light, another fundamental physical limit is related to the expansion of the universe. Due to the accelerated expansion of space, distant galaxies are receding from us at speeds greater than the speed of light. This means that light emitted by these galaxies will never reach us, creating a cosmic horizon beyond which we cannot observe. The expansion of space itself is also stretching the wavelength of light, causing distant galaxies to appear redshifted and making it difficult to detect objects at extreme distances. Technologically, there are limits to the sensitivity and resolution of current telescopes and instruments. Despite remarkable advances in technology, even the most powerful telescopes like the Hubble Space Telescope can only observe objects that emit light in certain wavelengths and under specific conditions. While next-generation instruments like the James Webb Space Telescope will expand our ability to observe in infrared, technological limits will always constrain how far and how accurately we can peer into the cosmos. Furthermore, the challenge of observing extremely faint objects, such as the earliest stars or distant galaxies, remains significant. Advanced observational techniques, such as gravitational wave detection, might offer alternative ways to probe the universe, but they also have their own set of limitations. Philosophically, the limits of astronomy raise important questions about the nature of scientific inquiry. To what extent can we ever truly understand the universe's origins and its ultimate fate? Can we explore every corner of the cosmos, or are there inherent limitations to our knowledge? These questions remain at the heart of ongoing scientific debate and exploration as we continue to push the boundaries of what is possible in understanding the universe.